This next set of notes is about pipelines. So we're going to start with some theory and then build out a pipelined CPU and then talk about some of the implications, including stuff like branch prediction and out-of-order execution and a lot of other cool things. So we start with a conversation about laundry for some reason, but the idea is to motivate pipelining in a CPU processor. And you wouldn't do your laundry like this. By the way, a lot of these figures and stuff are from the Clements textbook. This is a great textbook. This is the one I use for a lot of this stuff. If you have access to it, that's great. You'd never wait until you finished putting away one load of laundry before you started washing the next load of laundry. Instead, you do this, right? You start one load of laundry and then you come back. I'm assuming people do laundry these days. You come back and then put the first load in the dryer and then start the second load so that washing and drying is happening at the same time, right? And then the third load, washing is happening, you're drying the second load and you're folding the first load and then you're putting away. And so the idea is you find parts of any process that you can do in parallel. Often this means you have to have multiple different functional units or maybe different people or different machines to do parts of the process. As long as each machine or person can operate independently, then you can start to overlap execution of some of these processes. And this is what gives us the idea of pipelining in CPUs. And it's not a new concept. People do this in a lot of other contexts, right? In a restaurant kitchen, one person's doing sauces and one person's doing vegetables and one person just spending their whole day peeling potatoes so that you can part by part assemble a meal very quickly because everybody's doing their own thing. Airport security is another good example, right? You don't wait until one person's boarded the plane before you start the next person through security. You have teams of people. Some people are doing the baggage check and some people are doing the scan, and all of this stuff happens so that you can get people through as fast as you can. The car assembly line is the classic example, but the other one is attending a concert, right? You have multiple things you do. You have to get in the door, and then you have to get your ticket scanned, and then maybe you put your coat in the coat check, and then you find your way to the, buy a beer, and then you go and sit down. You wouldn't wait till one person sits down before you let the next person through the door. All of these things happen in parallel. So it's a form of parallelization. But it's not perfect, right? Sometimes some processes that are marching through the pipeline might be a little bit different. In the laundry example, if you discover that that there's a stain on a shirt you got to wear tomorrow, then you stop doing everything else. You put that shirt back in the washing machine again, and everything has to wait. So the other challenge with building a pipeline CPU for instruction handling is you got to know when there's going to be problems and invent ways to fix those problems. So we're going to break our machine that we built down into some subtasks that should take about the same amount of time. They should be independent of other subtasks, and they should be able to operate in parallel. And each complete task should use all the subtasks in the same order. Now, these are really, really strict constraints, but they give an idea of how to actually put this stuff together for a first pass, and then we can relax some of these constraints as we figure out what things work well and what things don't work well. Here are the things that you might want to be aware of, right? There are, taking into account these requirements, that things should take about the same amount of time, be independent, parallel, and be in the same order, we know that's not true. Already we know that things take different amounts of time, right? Multiplication takes a lot longer than addition. Loading and storing takes a lot longer, right? All of these things take different amounts of time. Often we find ourselves in a position where doing one instruction relies on the output from the previous instruction, right? You're going to compare two numbers, right? Maybe you subtract two numbers, and if the result is 0, you take a branch. Well, that means that the subtraction has to complete before the branch can start, right? That undermines the whole idea of pipelining. And in the previous machines that we've built, we use a lot of components the same time. We use components over and over again, right? We use the register file multiple times. We use the program counter multiple times. If we were calculating a new program counter as the result of a jump, maybe you do the ALU to compare to decide if you're going to branch but then use the ALU again in the same instruction to calculate the new program counter. So there's a lot of instances where these fundamental assumptions don't hold. And so we may have to rethink some of the ways that we do assembly language programming to be able to have these features actually work. So we're going to start with a very simplified version of our machine. In previous conversations, there is this idea of Harvard architectures versus von Neumann architectures. Harvard architectures, the idea is you split up operations into parts that you need, specifically that instruction memory and data memory are separated. In early conversations about architecture, you might think that this is a fairly silly thing to do. Why not just put everything in the same place? And in reality, in our computers today, if you look at main memory, it contains both data and instructions. And there are good reasons to have data and instructions in the same place. If you want self-modifying code, you will be able to store information in the same way that you access it, data versus instructions. But we can't pipeline if we're going to do that, because we want to be able to do data access at one time while still loading the next instruction at the other time. So in this case, Harvard architecture is going to be not as useful, and so we're going to move to von Neumann architecture. Other way around. Von Neumann architecture, where everything's in the same place, is going to be not as useful. And so we're going to move to Harvard architecture, where we can split things apart and access them separately, right? So this is going to be our basic abstract machine. We're going to access instruction memory, then we're going to access the register file, then we're going to access the ALU, then we're going to access data memory, and then we're going to access the register file a second time to put the result back. This is a thing that often tricks people up, is that we're not actually doing 5 things in a row. We're doing 4 things and then doing the second thing again. Register file access, we have to get information and then put information. Each one of these phases is going to correspond to something we can overlap. And again, this assumes that every instruction has memory access, which it doesn't. This assumes every instruction does write back to the register file, which it doesn't necessarily. But if we can abstract away all of that stuff for now, we can look at this and say, we're going to fetch, then read, then execute, then access memory, then write. And this is a very standard, simplistic 5-stage pipeline that we use for education. And in fact, the RISC-V machine uses this 5-stage pipeline because it is simpler and easy to understand and easy to implement. There has been a trend of more complicated pipelines. This is the Cortex A8 pipeline. It's got a lot of stuff we haven't talked about. It's got instruction issue. It's got a superscalar, many different execution functional modes, lots of different things, and individual instruction execution functional units like floating point, multiply, they themselves might be pipelined. So in reality, it's much more complicated, but in our simple world for now, we're going to keep it simple and use a 5-stage pipeline like this. So the way we're going to do this, and this will start in the next video, is we're going to take a simple single cycle machine and we're going to break it up into pieces. We're going to break it up such that each part of the machine is more or less independent. And then we're going to figure out how to get data from one place to another, because if the ALU is doing a different instruction than is being fetched by the instruction register, we got to make sure that the ALU has the data it needs to do the work that it needs to do. So we have to carry that stuff along with us in the pipeline. We have to carry along control information. We have to carry along data. So each clock cycle, theoretically, the instruction moves to the next portion of the pipeline. So that's what this looks like. We're going to split it apart. We have these registers already. The program counter. We have the program counter, which is sort of holding information to present to the instruction memory. And then the result comes into the instruction register. So we have this idea already of holding information on 2 sides of an operational unit. So holding it in the program counter and then holding the result in the instruction register. And then we just do that again. We hold the information for the register file in the instruction register, and then we need to insert a register between the register file and the ALU to hold the result of fetching those operands. Then we need a register to hold the result of the ALU, And then we need a place at the end to put the result when we're done either executing or grabbing data. And you can see here already we've added a little bit of a sub switch to say, sometimes the result comes from the ALU, sometimes the result comes from data memory. We might need to put one or the other of those back into the register file. But the neat thing about that is that the register file is the last register or it's the last latch of the pipeline, because that's where we put the result back. We retire the instruction by putting the result back in the register file, assuming that we are storing something. That's the last thing we do in the instruction. And so we've got program counter, instruction register. These are now pipeline latches. And we've got 2 more pipeline latches, source for the input of the ALU and result for the output of the ALU. And we recognize that some of the stuff we did when we built the multiple pipeline machine, where we had a memory data register and a memory address register holding values between, before and after the memory, same kind of idea. We're holding values before and after the ALU so that it can run independently. So this is our sort of theoretical structure we've got set up. In the next video, we'll start building it.